In the previous videos, we looked at Riemann sums, which you use to find the total amount of something that accumulates when you know a rate of accumulation. In this video, we'll look at a way to improve your estimates. In one of the previous videos, we found the total amount of dust that accumulated on the Mars rover's solar panels. If R of P is the amount of dust in milligrams that the rover accumulates for each kilometer, then we can write this in Riemann sum notation as the sum of R of P times delta P. We assumed that the rate of accumulation was constant, but this isn't necessarily the case. So our estimate of 260 milligrams isn't particularly accurate. To find a more accurate example, we'll need more data points. For example, we might know the rate of accumulation at all of the original points, and also the rates of accumulation at positions halfway between the original points. We could use the same method as before to find the amount of dust that accumulates over each interval. This would give us an approximation of 278.75 milligrams of dust that accumulates over the entire 100-kilometer trip. We're still assuming that the rate of accumulation stays constant over each interval. However, since our intervals are all smaller than they were before, this assumption doesn't impact the accuracy of our approximation as much. So this new approximation, 278.75 milligrams, is closer to the actual amount of accumulated dust than our previous estimate was. This process of using a larger number of smaller intervals to get a more precise answer can be thought of in terms of limits. To get the most accurate approximation of the total amount of dust that accumulates, we can take our rate of accumulation at position p kilometers from the start, which we're writing as R of P, multiply by the length of each interval, which we write as delta P, and then add up all of these amounts of dust. As we make the interval lengths, the values of delta P smaller and smaller, which we write as delta P goes to 0. These approximations get better and better. They get closer to a number, in this case, the actual amount of dust. And this number is the limiting value of this process of using smaller and smaller intervals. We write this as the limit as delta P goes to 0. When delta P gets small enough, we think of it as dP. Also, when all of this happens, instead of adding up 6 or 12 amounts of dust, we end up adding, essentially, the amounts of dust accumulated for infinitely many tiny intervals. To notate this, we change the summation symbol to an elongated S. This new notation, which we call a definite integral, is another way of writing the total amount of dust that would accumulate if you added up the amounts of dust that accumulate over all of the infinitesimally narrow intervals between 0 and 100 kilometers along the rover's path.